Now please note in activity 4.5 we're going to be making use of the printouts from the worksheet, so please make sure you have that ready. Also make sure that you've got your calculator on hand and you're able to produce log functions pretty readily. So you can see my function of the log x to the base 10. It's undefined in the negative, has a vertical asymptote at x is equal to 0, rises up dramatically until we have the log of 1, which is defined as 0, and then keeps on increasing, albeit very slowly, according to your graph there. Now, another thing you might like to note is that this graph is really a reflection of the 10 to the x function. If I maneuver that and I also plug in y is equal to x, you can see that the log function is a reflection around the y is equal to x line. That follows the notes that you have on page 1 of your notes there. In a moment, I'd like to take you through question number 1, how we can actually process it. Notice how we deal with the graph of y is equal to log x. When we have an asymptote, horizontal asymptote there, or a plus, we actually move it up as we go along. Just briefly discussing page 2 of the notes, you can see what happens as we have a dilation factor. It increases, the graph still cuts at 1, 0. But the second point I've chosen, x is 2, increases with a half. Obviously it decreases. And when we're taking log to base 10 of multipliers here, you can see the dilation factors at work. Translation, x minus 1, you can see how I've had a translation to the right there. X minus 1, on the other hand, brings it all down. And finally, the reflection basis. When I have a reflection negative x, it's reflected around y. And when I take the opposite of a log function, of course, just as you've seen before, the function is reflected around the x-axis. So some good little pointers to hang on to as you do this work. In question 1, I'm going to look at the log x to the 10 and 2 log x to the 10 because they'll share the same x-intercept, obviously have the same domain and the range there as well. What will change is the second point that I choose. So in this case, the x-intercept, y-intercept, sorry, x-intercept, get it right, Gary. That happens at 1, 0. So in this instance, plugging in y is equal to 0, that will occur when x is equal to 1. So in the first and second instance, I'll have the x-intercept y is equal to 0 at 1, 0. Our second point, I'll choose when x is equal to 10. So in the first instance, y is equal to log 10 to the base 10, which is 1. So I'll have a point of 10, 1. And the second instance, when I do that twice by 1, which will give me 2, 10, 2. And that will give me a way of plotting those two graphs. So the first graph and the 2 log 10 to the x graph will look like so. Now, when I deal with y is equal to 2 log 3x to the 10, the x-intercept when y is equal to 0, so I therefore have 0 is equal to log 3x to the 10, so therefore 10 to the 0, which is 1, is 3x, and x is equal to 1/3. So instead of 1, 0, I'll have 1/3, 0, and my graph will hook up like so. A second point, to choose a second point, I may as well choose the value of 10. So when x is equal to 10, y is equal to 2 times log of 30. I'm doing this on a separate calculator. So 2 times log of 30. I end up with 2.95. So that 10, 2.95 will be the order of the day. Replicating that on the calculator, and please make sure you are doing this on your calculator, you can see the log x to the base 10, the 2 log 10, 2 times dilation, and what effectively is almost a 3 times dilation in the third instance.